notes, do you have this cool picture?
Yeah.
What's it look like?
The Middle East.
Yep. What's it showing?
Slope field.
Okay, it says slope field. It says vector field. That's interesting.
The winds.
The winds, right? So wait, does the wind like go and then like it doesn't go? Then it goes and then it doesn't go, and then it goes and then it doesn't go, and then oh, it's over here, and then oh, it's over here, and then what is this showing? Motion. It's showing movement. It's showing, what does the movement look like? Curves. Wait a minute. If these are like the slopes of curves, what technically are each and every one of these little directed line segments?
Tangents.
Little baby tangents. So I have a field of slopes or a field of tangents. So I'm going to draw little baby tangents, and what is the purpose of drawing little baby tangents? Well, if you can't necessarily know a function that models the movement, can I still take the rates and figure out the direction of the rates, etc., thinking about vectors? We're not going too crazy in physics, but can you model the rates and then see the flow through the rates, even though you can't actually get the equation for it? Yes. Hence, slope fields. Now, slope fields, let's go back to here. So when slope fields are graphs of little baby tangent lines, which put together can show me, wait, put together, how am I going to find slopes? Well, guys, where do slopes come from? Differential equations, because differential equations are equations of derivatives, which shows us slopes of tangents, right? If I get a graph of lots of little baby slopes that are determined by a certain differential equation, then I can have a visual perspective. What? I can see the original, even if I can't find it. I can see it. I can see how it behaves, how it moves, how it changes, etc., etc., etc. Now, by hand, if you guys look, do you have the worksheet kind of close?
Yeah.
Don't take it out for like permanent, but just look at it real quick. What do the first 6 problems on there look like? It's dot paper. We can like do the dot game and draw little lines and put our initials in it. No. We have a fun game, although it is a fun game. It's a good game. But, coming back. It's not for the dot game, it's for slope fields. Kiddos, if I asked you how many slopes we would have to show in this following example number 1 on your note packet. Sorry, I was just showing you the worksheet. Example number 1. Do you see it? I think it's example 1. Isn't it example 1? Yes. Okay, example number 1. It has a graph of this size. If I told you show me all the tangent lines possible in this field, how many would you say that there were?
1.
No.
Infinitely many.
Infinitely many, but am I going to make you do infinitely many? No. So look at what you have. Am I going to literally do it for like -1/2 and for negative, and I'm going to do all these in-between fractional ones? Or am I just going to do like a dot paper and say, hey, let's just do the whole numbers? Now, how many slopes does that still mean? How many little baby tangent lines am I going to have to find? Well, you can do better than that. You guys are in calculus. How many?
Enough.
What doesn't include 25?
Yep, 25. Because it's a 5 by 5, right?
Yeah.
5 across, 1, 2, 3, 4, 5 down, 5 by 5, 25. Okay. So I'm going to have to find 25. Hold on, by hand. How does it say we have to start? I know that's a really fun. Hold on. How do I start by hand? Make a table showing slopes. Table, slopes, points. Table of slopes and points. Okay. Table of points and slopes. Now, hold on. It's not going to be as bad as you think every single time. There were a lot of conditions in what I just said. But it's not going to be as bad as you think every single time. And actually, last year after the actual AP, kids were like, there was a slope field, and they were excited on the FRQ because it's easy. You just have to get the hang of it. Okay. It's not every year, so it might not be this year, but it's at least a multiple choice if it's not FRQs. Hold on. Guys, pick a random point that has a dot on it. Go.
1, 1.
0, 0, 0, 0.
Okay, I heard 1, 1, and 0, 0.
1, 1.
1 minus
1 minus 2? Oh, 1 negative 2? That's random. I would have thought you guys would have either like started there or there. No? Alright. 1, 1. That's random. Okay, anyway. Kiddos, if I want to find the slope at 0, 0, I plug into the differential equation and I say, oh, hey, the slope is what? 0. Why? Because you plug in x and 0 squared is 0, so therefore 0. What does that mean my little baby tangent line is going to look like? dependent on x's, which means I don't really care what the y's are when I plug in, which means if I go to another point, like say 0, 1, what's the slope? What's the slope going to be?
0.
How about 0, 2?
0.
How about 0, 3? Oh, well, we're not going there. 0, negative 1. 0, negative 2. What are all those slopes? Well, all the x's are 0, and it's only dependent on x's, so maybe we just found our first trick for slope fields. If it's only dependent on x's, x equals 0 is going to have the exact same, the entire line. They're going to have the exact same slopes. True?
True.
So let's not work too hard. Let's go to another x equals. What do you guys want? X equals 1, 2, negative 1, negative 2. 2. All right. So if x equals, shush. If x equals 2. Actually, I would rather go to 1s. Can we go to 1s for a second? There's a particular reason why. Hang in there. I'm going to go to 1s. If I go to 1s, question, what's the slope going to be? 1. Wait, how do I, Well, at 1, 0, can I go up 1 over 1 and say I don't want the whole thing because otherwise it's going to run into the other little baby tangent lines, but I can do like an approximate, right? And then we just saw that the pattern exists if it's only dependent on x's, then all the x's, hey, they're all going to be 1s, 1s, 1s. Now, to some extent, you can't make it perfect, but you can make it relative to the points around it, meaning slope is 0, slope is approximately 1, up 1 over 1, right? What's going to happen if I go to negative 1 in all of those? Negative 1 squared is still going to be 1. So guess what? All of these are going to be up 1 over 1, 2. Sorry, also. Tambien? Okay. Thanks. How about over in the 2's? My slopes are going to be 4, right? How did I do 4?
Take a guess.
Can I go down 4, left 1, and say, oh, hey, and yes, kind of it's a guess, but it better be steeper or else, right?
Wait, what?
If I say a slope of 1 and a slope of 4 are the same, I'm having some issues. I went rise over run, down 1, 2, 3, 4. Negative 4, negative 1 means a positive 4. And I went approximately little baby dotted line, and then I'm going to go and try to keep it somewhat relative to the points around it. And if I plug in negative 2, do you guys see the pattern? Negative 2 squared will still be a positive 4. So up 4 over 1, little baby dotted. There he is. Question, what if I am playing teacher right now and I'm making up a problem? What if I gave you an initial value? That means you should be able to pick out of a family. This is a family? It's totally a family of antiderivatives. You should be able to pick out a particular one, right? So if I give you a point and if you have a slip field because either you can't integrate or you're not integrating at the moment, how do I see an original? How do I show an original? Well, first of all, a point, that's easy. 1/2 1. Ta-da! Then what? Well, then I say, you know what? I follow the curvature. This is not like Minesweeper, so if you accidentally hit a tangent line, you're not going to blow up. It's okay.
Oh, wow.
Oh, wow. Why does it make sense that my original function, kind of following the movement, right, of the slope field, you might say, I would have gone that way. I don't care. That's fine. Go that way. Okay. You just have to have the general curvature, okay? I have to have a horizontal tangent line, so flat right there, and then it's going positive, and it's coming from. Okay. Why does it make sense that it would look like a cubic?
Because it was a cubic.
It wasn't a cubic, aka the differential equation wasn't a cubic, but it was a squared, and the original would be a cubic, right?
Yeah.
Now, obviously, this is one, could you have integrated? Yes, you could. X cubed over 3, and then you would have plugged in, right? But we're getting ready for maybe those you couldn't. Cool kids, take it away. y equals negative x? Why does that make sense? Because y and x are added together, so you're not going to be going straight up and down like the last one where we were able just to copy it and say, hey, x by, x by, x by, when x is 0, x is 1, x is 2. When you have x's and y's, it's going to go in a different pattern. Benji, go ahead.
So one would be like really, really slanted. I mean like almost straight.
Well, see, I have like a slant of, what are these ones approximately? -1, down 1, over 1, right? But then this one was negative down 2 over 2, so I had to make it a little bit steeper. And then this one would be down 3 over 3, a little bit steeper. So you kind of just try to make them relative just to get the general point across. Cool kids, what's so nice about this one?
It's baby size.
It's a little baby one. So, what do I do? Maybe you notice that I'm not just trying to show you how to make one by hand, but also the difference of differential equations with only x's, differential equations with x's and y's to the first power, differential equations with x's and y's squared. We're going to do this one really fast. Oh, did it give me a point? It did. I totally failed. Guys, hold on. There was an initial condition. What am I supposed to do with him?
Plug it in.
Kind of. To my graph. So 0, 1 would be 0, 1. Wait a minute. Hold on. How do I? Well, he's going up somehow. Remember, it's not Minesweeper. He has to have like a horizontal tangent, right? And then he has to, it's going to be something like this.
Whoa.
So they don't have to be like direct down the line.
No, they don't have to be directly on the line. And technically, I think I should move him a little bit more like this. Because it is possible even sometimes to have ones that move or behave differently depending on what part of the graph they're on. Anyway, but those ones aren't the ones with my initial condition. Struggle.
What the?
I know, it's my fault. I'm going to get rid of the other two because that wasn't with my initial condition. You just kind of have to follow the trend as best you can. Thanks, Emily, for the question. Here we go. If I plug in, I have x, y. Guys, I'm not even going to make a table because hopefully we're tracking with what to do. If I plug in 0, 0, 0 plus 0 minus 1, it's a negative. Okay? If I plug in 1, 1, 1 plus 1 is 2, 2 minus 1 is 1, so it's going to be up 1 over 1. If I plug in 0, 1, 0 plus 1 minus 1, he's flat. If I plug in 0, negative 1, negative 1 gets squared, plus 1 will be, again, 0. If I go, wait, do I fail at math? 1, 0. No, hold on. 1, 0. 1 plus 0 minus 1. He was flat. Negative, I know. Negative 1 squared is 1. 1 plus 0 minus 1. He's flat. Negative 1, that's 2. 2 minus 1 is a
Wow.
positive 1.
Yeah.
Negative 1, they're all going to be positive, so that's going to be a positive 1. That's going to be a positive 1. That's going to be a positive 1. Anyway.
It makes sense.
Sketch the solution curve that passes through the origin. So, well, passes through the origin. All right, fine. He's going down, right? Wait, he has to have like a horizontal? Huh. Then he has to have like a, maybe?
No.
Do you see how the fewer points you have, the harder it is to figure out what's going on?
A little bit.
A little bit, huh?
Little bit.
Which is why the more slopes, the merrier when you're trying to make family of anti. Oh no, what is going on? Guys, if you were thinking about your notes, didn't we write down something like problems can change, problem types can change?
Yeah.
And that's what I was showing you in these ones. And this is where we're pretty much going to camp out tomorrow with lots of examples. Hold on. We need to match the slope field with, we're given the slope field,
Oh no.
and we're looking for the original. Hold on. What forms a slope field? Slopes, tangent lines, differential equation. What do you see moving through a slope field? The graph of the original, which is what we have as original. So guys, hold on. If this is an original, what does he look like?
Sine.
Yeah, right? But hold on. What if we were looking for his differential equation? What would that look like?